Okay, the previous part, which is part one, was on linear regression. Now we move on to correlation. And when talking about correlation, we actually are talking about correlation coefficient because the correlation coefficient R determines whether or not we have correlation. Before looking at this formula, I'm going to talk about R, which is the correlation coefficient. When it is less than 0, you have a correlation between X and Y, and that correlation is negative. So if the correlation coefficient is less than 0, you have a negative correlation between X and Y. If the correlation coefficient is greater than 0, meaning it's positive, and then you have a positive correlation between X and Y. Another way to say that is if R is less than 0, then X and Y are negatively correlated. Otherwise, X and Y are positively correlated. But if R is 0, then there is no correlation whatsoever between X and Y. Now let's go to the definition of correlation coefficient. This might look intimidating at first sight, but it's actually very easy. And what you need to note is this. You see this term? You will see this term is actually familiar. Let me do what I like to do, which is to use different colors. You see that? These two terms are actually very familiar. If you recall this equation which we all learned from high school, this is z-score. It basically normalizes your data. So if you have data in this format X, and Y, I have all sorts. These are your I's. So I is 1, 2, 3, and you have lots of data in that form. So you normalize each of the X's by doing a z-score transform this way. You get the mean, which is X bar, then subtract the mean from each of these X's. That's what this is. The denominator is just the standard deviation of this. So standard deviation of this is sigma X. Do the same for Y, you get the z-score transform of the Y data. It's just normalizing the data. Now, already you can see this term. Maybe I should use highlight here. You see this term? Same deal as this term, right? If we move on to the definition of this term, your standard deviation, which you all know, right? This is your standard deviation. And looking at your standard deviation, you see this? Same as this. It's not allowing me highlight. Okay, good. Same as this. So we've already accounted for this term right here, because it's z-score divided by standard deviation, but this term is missing and we're going to account for it shortly. And if you look at the other term, I'm going to also highlight, but use a different highlight color. I'm running short of ideas. Yeah, so this is this. That's your zy. This is also this, which shows up here. And you can substitute these three equations. I mean, these three equations right here. You can substitute these three into this and get a simpler form of the definition for your R, which is this. So it's just product of your z-scores, which are defined here. Sum them up, sum of the product of z-scores, and you normalize by n minus 1, which doesn't show up here. So that's precisely what your correlation coefficient is. It's essentially a product of z-scores summed through for each data point. And this is just a normalization constant. So R is a normalized sum of a z-score product, like I explained. So correlation is basically all about z-scores, because your correlation coefficient, like I just showed, is a product of your z-scores. So from the sign of your z-scores, you can take a product and you get what the sign of your correlation coefficient will be. And how do you get the z-score, the sign for these different z-scores in this quadrant? Well, this is your x-axis, right? This is y. Let me do a better job here. I'm gonna erase. How about we use black? So that's your x-axis, y-axis, and this is your origin at 0, 0, right? That's your origin. So let's pick a different color. So this is your x-axis. Above your x-axis, meaning as you go here, what's the value for y? Y will be positive. So z-score above this will be positive. So you see your z-score positive, z-score positive above. How about below? It's going to be negative, right? Is that what you see? Yes, z-score negative, z-score negative. Now let's clean off that and look at z-score for x. So clean this so we don't mess up everything, and go back to this, and now we are looking here. That's positive x, right? To the right of that y-axis, x is positive, so x better be positive. X, z-score for x has to be positive, and on the other side, yeah, it's going to be negative. Now take a product of those two. Minus times positive, minus, positive times positive, positive, positive times negative, negative, negative times negative, positive. And the sign of this product will be the sign of your correlation coefficient. So this will be the sign of your correlation coefficient. And it makes sense, right? So if your line, let's use a different color. If your line were to go through these quadrants where R is positive, so this is your line. I know it looks like a wavy line, but let's assume this is a straight line. Yes, that will be a line with a positive correlation coefficient. The slope is positive, right? For as x increases, y also increases. So y increases as x increases. Correlation coefficient will be positive. On the contrary, if you had this as your regression, linear regression line, now you're passing through these quadrants where the product of the z-scores is negative. So your slope will be negative and your correlation coefficient will be negative. So there will be a negative correlation between your x and your y, and that's what I summarize right here. Sign of your correlation coefficient, the same as the product of the z-scores. Now, what does different magnitudes of correlation looks like in your data in graphical form? So in graphical form, I've shown some different correlations and show the corresponding correlation coefficient. So if R is positive and it's as big as 0.9, then there is a very strong correlation, right? The maximum R can be is 1. So 1 will be perfect correlation. And so here you have a strong correlation, almost perfect. And the data points are very close to the linear regression line. This one is weaker. It's also positive because R is positive, but it's 0.6, much less than 1, right? So the data is a little farther from your line, and that's a weaker positive correlation. Now, if your line, on the other hand, has a negative slope, like shown here, with a perfect negative correlation because R is -1, the maximum magnitude is 1, so negative, then your data is very close to the your linear regression line, your line of best fit, the red line, very closely fits your data set. And this will be the case where it's weaker. So this is a weaker negative correlation. Your line is a little farther from some of the data points, as explained previously. What if R is absolutely equal to 0? Then there is no correlation whatsoever. You can't draw a straight line through this data set, right? This is like a cloud. Do you want to draw it this way or this way or this way or this way or this way? It's a cloud of points. There is no correlation between X and Y. Now let's talk about properties of your correlation coefficient. We're going to talk about this more later, but I'd tried to explain this before. If you add X and Y by varied data, right? And this is your I, just the index 1, 2, 3, and you have so many of those. If you go in and you multiply each value here already by any constant value, which is positive, say 2, your correlation coefficients will not change. That's what we're showing here. Correlation coefficient doesn't change when you multiply your data set through by a constant. It just shifts the entire data set, the data plot. So if you add a line here going through some data points and you multiply all of the x's, so the x is this axis, right, by say 2 or any positive constant, what it does is it shifts the line. The red line moves from where it is right now to the right, because it's positive, and it shifts everything that way. The slope is still the same. All the data points also moved with the line, and the correlation coefficient remains the same. And I'm going to show this in the Python code. Same deal, if you add a constant to each value. Now my stylus isn't working anymore. Let me pause this and figure that out. Okay, I'm back. Got the problem fixed. So it moves both the data and the line to the right. And like I said, I will show this again in Python. What if you add a constant value to everything in X, or say everything in Y? It's going to also move the entire line and the points, and correlation coefficient, which is the R value, doesn't change. What if you swap this? So x becomes y and y becomes x. Well, correlation coefficient will also remain the same. So correlation coefficient will not be changed if you multiply by a positive constant. If you add a positive constant or negative constant, any constant value, you add it or subtract from your x or y, correlation coefficient doesn't change. If you interchange x and y, correlation coefficient doesn't change. And this is important. I ask this a lot on the quizzes in the midterm finals. Okay. Last thing here is that correlation coefficient is only meaningful when your data looks like a straight line, as shown here. If your data looks like this, like the blue dots here, obviously you can't fit a line through this, right? You can't fit a line through this. The data itself is non-linear, meaning not like a line. So you're going to need a non-linear model and not a linear model. So it doesn't work. Correlation coefficient does not apply when you don't have linear trends. Another weakness of correlation coefficient is outliers. All of the data points are here, so the line of best fit would have looked like this, or maybe even like this. But there is a data points far out here, and that will mess up your quality of best fit. So the quality of the least squares line that passes through this data will be poor just because of this. Why? Remember, it's a least squares line. We are minimizing the least square error. And how did we calculate the least square error? If this is your line, you're going to take the difference between the model prediction, right? Which is this. Very large, right? Compared to these other ones, which are close. So this very big difference will overwhelm the regression fit. When you square this y minus y hat, right? When you square this, it becomes so large in comparison to the square of this error and these other ones. So this will pull the data, it will pull all of this line towards the outlier, and the quality of the line becomes very weak. I mean, how well does this line fit through this data? Because this is actually the important stuff. So whenever you're going to use linear regression, first thing you want to do is to remove outliers like this. Even this could be considered an outlier, and then you can possibly fit a line through the meaningful data set. So I'm going to take out all of these. So if we had first taken out this and this, then your line of best fit could have gone this way, and that would be a better model. So that's one weakness of linear regression, and also the use of correlation coefficient. Very vulnerable to the presence of outliers. Very important message here. Correlation does not imply causality. That two variables are correlated doesn't mean one variable is responsible for the change in the other all of the time. And this is an example. One variable is number of women with bachelor's degree awarded in engineering. Second data point or data set, total US crude oil imports. Both of them are plotted here. The red is the women bachelor's engineering awarded. This is the total US crude oil imports. You see they follow each other. So if you were to cross plot them, so one on the X, one the other on the Y, the data will pretty much go along a straight line. And when you draw that straight line through it and calculate the correlation coefficient, it will give you this value, which is very high, right? Strong positive correlation. Does that mean if More women get bachelor's degree in engineering, total crude oil in the US, total US crude oil imports will increase? No. So the fact that two variables are correlated doesn't always mean one is responsible for the change in the other. Correlation does not necessarily imply causality.